preserve a subgroup of the normal group, also normally supersymmetries, and they are amenable for a holographic description. This will be particularly useful if you are interested in a coupling regime of these defect conformal field theories. So in these realizations, when you study defect conformal field theories in holography, typically you have a low-dimensional field, that is the defect field theory, realized in some brane intersection, which consists on two branes, what we call the background branes. These are backgrounds, which intersect in higher dimensions compared to what happens when you include the defect branes, and that in the near horizon limit give rise to some ADS space which has higher dimensionality compared to what happens when you consider the intersection of the background branes, but also this other set of branes that I refer as defect branes. The whole thing will give a lower dimensional intersection where a lower dimensional field theory will lead, which typically will give rise to some conformal field theory in the IR. So in the geometrical side, what happens is that this lower dimensional ADS will arise in the near horizon limit of the whole brane intersection. You include the background branes and the defect branes, will locally, when some direction, non-compact direction, because in these realizations you always have a non-compact direction that when you send typically to infinity, problem when you want to describe the field theory, but this is part of a higher dimensional ADS space, which is the one that arises in the near horizon limit of the direction containing only the background branes. Okay, we say that this ADS geometry arises asymptotically locally when we send this coordinate to infinity, because it contains extra fluxes that are to the defect branes. These fluxes don't disappear in this limit, but they contribute in a subleading way to the equations of motion. Notice that this is different from an RG flow, because in an RG flow we would have some solution which in the UV gives rise to a higher dimensional ADS space, and in the IR to a low dimensional ADS space. Here we have an ADS, a low dimensional ADS space, which only in the UV will become asymptotically locally a higher dimensional ADS space, but not a, I mean, this, it's important to emphasize this asymptotically, because still there you can see the presence of these defects, only in a way. So as I said already, when you want to your ADS, your low dimensional ADS space, you don't know yet whether this maybe this defect CFT. What you see is that there is a non-compact direction that is complicating your life, because when you want to describe what is the field theory associated to this geometry, this non-compact direction, you need to define it in some way in order to define your low dimensional theory. This is interpreted when the theory is associated to a defect CFT as the need to complete CFT by the higher dimensional one away from the defects. In some sense, this non-compact direction, when it goes to infinity, you end up in the higher theory, and in the opposite limit is when you are, say, at the core of the. So. These are supersymmetric constructions. The examples that I will show you, there are different numbers of supersymmetries that will be preserved. You have some superconformal group that the CFT has, and typically you realize this with some supersymmetries. Yes. So when it comes to identifying dimensional ADS spaces that may have an interpretation as being dual defect CFTs, of course, when you are in low dimensions, there are many possibilities for ADS2 and ADS3 spaces. Classifying these low-dimensional ADS geometries is especially challenging because you have a very high, a very large internal space, and therefore many possibilities for geometries, topologies, and symmetries. So in the particular case of ADS3, which is discussing here, there have been partial classifications of these geometries with various numbers of supersymmetries realized in both sectors, in one of the sectors. Some of these classifications are complete, some others are partial. Many people have contributed to this. Here I will be focusing on some recent classification that was Neil McPherson and Anayeli Ramirez a couple of years ago. They classified ADS3 solutions with 0.5 and 0.6 supersymmetries. Here, the notation is such, I will mostly focus on the 0.6 case. The notation is 6 means 6 Poincaré supercharges, so you would have to add the superconformal generators. In total, you would have 2 supersymmetries. So, in recent years, some of these ADS3 that were already classified or were just found, ADS3 and ADS2 have been proposed as dual to defect CFTs. In some of the realizations, it has been possible to embed the defect CFT within the final theory through explicit quiver-like constructions. With this means, you have your higher dimensional conformal field theory for which you have an description, and you see that when you add the defect branes, you are actually alerting some extra degrees of freedom in your quiver, and you find your construction for your defect theory, which is now describing a lower than CFT in the IR typically. And these are very nice pictorial realizations, and I will be showing a couple of them. So in this talk, I will focus on the interpretation of the ADS3 solutions with 0.6 supersymmetry were classified by McPherson and Ramirez. And more briefly, I will also focus on some other ADS3 solutions extracted longer ago with 0.4 supersymmetry, and I will try to interpret both classes of solutions as these defect CFTs. For this class of ADS3 solutions, we will do something interesting because we didn't succeed in describing as dual to defect CFTs, but rather we had to give them an interpretation in terms of the construction of higher dimensional conformalities. So, well, this is based on recent work with a number of people. So let me start by giving the line. First, I will discuss the 0.6 solutions to massive 2A supergravity, try to interpret them as phase defects in ABJM. And then this will be like most part of the talk, but more briefly, I will discuss this other class of ADS3 with 0.4 supersymmetries, also to massive 2A, and we will see that we can interpret this as the construction of 61 CFTs. So we start by discussing the ADS3 solutions to massive with 0.6 supersymmetries. These are solutions that are foliations of ADS3 and the complex projective space on an interval, which preserve 0.6 supersymmetry with this superconformal group, SO6 R symmetry, that is realized geometrically on the CP3. I'm going to argue that these solutions can be regarded as an extension of the ABJM. I will be saying, but it's all the time the ABJ extension, rather, to the massive case, introducing the 8 branes. This will make that one of the external directions, one of the in the ADS4, will become an energy scale and generate a flow towards an ADS3 space. So let's see how this happens. The form of the solutions is quite compact. You have, this is the method, this is the ADS3 part, the CP3 part, this R parameterizes the interval. The solutions are defined in terms of this function h, which is function of R, and the first and second derivatives. We have a Neves-Schwarz-Neves-Schwarz2 form, which depends on this the Keller form of the CP. And here I have introduced this integer L, which is a large H transformation parameter, because this R is that lives in the interval, so in principle it is non-compact, and you have to make B2 satisfies the condition that it lies in the fundamental region, integrate over the non-trivial two-cycle that you have in the CP3. So in order to do that, you need to divide the R intervals in our notation, in our conventions. This is in L plus 1. When you are in L plus 1, you need to make a large transformation of parameter L to enforce this condition. This, by the way, is creating an NS5 brane at R equal L. Happens when you are doing a large gauge transformation. We also have all the fluxes that you can have turned on in massive 2A. 0, F2, F4, F6. I'm not giving the explicit expressions to match the slide. And this means that we are going to have, besides these NS5 branes that I was saying are located at R equal L, we have D2, D4, D6, and we have D8 branes. So in particular, the D8 branes play a very important role. This function H satisfies a Bianchi identity, which involves its third derivative in terms of the Romance mass. So this is going to be a cubic. And the most general way in which we can construct global solutions with these conditions is by gluing local solutions to branes. We are going to be introducing D8 branes at R equal L, where we have the jump in the Neves-Schwarz-Neves-Schwarz chart, the NS5 branes being created. And we are going to glue the D8 branes at these positions. Then H, which has 3 other remaining parameters to be fixed, we can fix constants in terms of the quantized charges of the D2, D4, and the branes that are also in the background. I didn't show the explicit expressions, but you can immediately relate them, expressions of these fluxes, to these quantized charges. So in the end, this is H function that you have in each of these intervals. In terms of the D2 charge, D4, D6, and D8. So with this information, even if we don't have the underlying brane intersection that gives ADS3 cross CP3 geometry in the near horizon, but you already have enough information from the fluxes to know to propose a Hanani-Witten brane scenario where your field theory will live. So we have in the R direction the NS5s, which are these lines. We have the D8s that we are introducing. They are and then looking at the fluxes, we can the D2s and the D6 are going to be stretched between the NS5 branes and have some orthogonal D4 branes. This is like a skeleton, say, of the Hanani-Witten brane intersection, because here we have a CP3, and this, as you know from the ABJM case, this makes it more complicated. So, yes. The coefficient of ADS, yeah, it will be depending. I mean, all these are. Yes. It depends on R generically. In the massless case, this becomes a coordination, but this H depends on R. These are, all these geometries are fibered on R. So in order to understand is the CP3 doing, how it's complicating this naive Hanani setup that I was proposing, we took the massless limit and see what happens case, when you remove the D8 branes. It turns out that in this case, this gives you simply ABJM. You remove the D8 brane, make a nice and simple change of coordinates to a new non-compact direction mu, and it turns out that this is what you build out of the ABS3 and the R part that now mu. And all these coefficients now related to your question, in that case, they are constants in the mass level. So you recover the ABJM metric. The Navier-Stokes form becomes the Navier-Stokes form that you have in the discrete holonomy of ABJ, and what you get in the massless limit. And in the massless limit, you know what is the brane setup that answers the solution. So this is better understood when you do a T-duality from type to B, because in that case, the Kaluza-Klein monopoles that are to the CP3, to the existence of the CP3, become 5 branes, and there you can really propose a Hanani-Witten brane setup and proceed with the quantization of the open strings and learn what is the field theory that you have. So this T-duality is done on a circle included in the CP3, which is this psi, and this makes that the that you had previous to the T, which are the color branes, the brane field theory leaves, now become these 3 branes that are wrapped on this direction. You have new NS5 branes. I have put them with a prime because already in the massive solutions that I was discussing, we had NS5 branes located in the R direction. These are new ones that come from the T-duality on KK that you have in your geometry. These are located in psi. And then you also have a bound state of an NS5 prime and the D6 branes that you had before the T-duality that D5 branes. So you have at psi equals 0 and 2, this is a circular direction, an NS5 prime brane, and at psi equal pi, this bound state, which is rotated with respect to their NS5 prime branes, with an angle that depends on this K. Okay, here I'm not showing the D4 branes because these, as you know, in ABJ are fractional branes. They are unstable. They decay to nothing, and they are not playing a role in the brane intersection. Maybe wonder why I'm using this n for the number of D3 branes instead of Q2, or K for the number of D5 prime instead of Q6. And this is because you may remember that in these non-trivial geometries, there are effects, which are the Friedel-Waaley and the higher curvature terms, which have the effect of solving higher dimensional brane charge in the work volume of functional branes. So when you are computing the quantized charge for D2 branes, you have the actual contribution of the D2 branes, this n, that is normally the number of field theory branes, the actual number of branes, and then also of the number of D6 branes that contribute through these effects. Okay, so this is why I'm using different letters there. Now that we know what's happening in the massless limit, we can compare our brane intersection with what we already learned from the analysis of the massive case. So we have
the solution in the type 2 brane.
When you do for ABJM, our solution is not simpler. You break some supersymmetry. The solution, the CP3, is like put into pieces. There's 3, there's 2, the interval. It becomes even more messy.
That's why you go for this hybrid thing. Started with the interactivity, but then you discover.
Yeah, it's as you do in ABJM. In ABJM, you also discuss background in type 2A, while the field theory, you discuss it in type 2B, because there is where you have a Hanani-Witten brane setup. Now we need to quantize strings, and then S5 branes impose boundary conditions on those, while the KK monopoles is not clear what they do. So typically, this you do when you find KK monopoles in your intersection. Duality and you. So yeah, we have this first piece. This is what in my introduction I was calling the background branes. But then we have extra branes that only appear when we switch on the mass. We have which is what we are introducing by hand, say, but then S5 branes also appear in the case of mass. Otherwise, they become the extra NS5s that you have in AVJ that don't play any role because they are unstable. Are not unstable. They have a charge and they appear in the massive case. So you see that in AVJM, the intersection is three-dimensional. Now, when we are introducing the D7s and in a way that the supersymmetries are preserved, the ones that you find at the solution, you end with a two-dimensional intersection. So this would be like our defect branes, and when you put all the branes together, the lower dimensional common brane. So if it was not by the rotation of this bound state, this whole brane intersection would preserve 0,4 supersymmetries. The rotation of the branes, as it happens in AVJM, reduces the supersymmetries to 0,3 in this case. See that we are, this is all half BPS compared to AVJM, because 0,3 here means 3, not 6 as. And this is because we are introducing this extra stuff. So, from this information, already draw what is our brane picture. See that here we have NS5 branes. We have these ones that are located in the psi direction, the one in which we did the T-duality, and these NS5s which are located in the R. And our color branes, the branes that have the lowest stability, where the field theory lives, are these D3s that are stretched in R and inside. So we have a brane box. If you are familiar with this, the realizations like extensions of Hanani-Witten brane intersections in which your color branes are stretched between NS5 branes in perpendicular directions. We have one of these things in which one of the directions is compact. So we can draw this in a way in which the R direction, if we freeze R, say, if we just look at this part, brane intersection, what we have is the NS5 prime brane at psi equals 0 or 2 pi. Here we have NS5 prime at psi equal pi, which forms a bound state with the D5 branes. Is here the number of these branes is. I'm going to explain this as you move in R. This should be like rotated to this, as in the AVJM picture. I didn't do that because I wanted to draw an eye, but this is rotated. And then here you have the that are stretched between 0 and pi, and after they cross D5 branes, they become, you add M, because these are the extra fractional D3 branes that you find in AVJM. Now, when we let R run, say, three branes become like plaquettes. You have like these plaquettes extended in R between NS5 branes that you have at these values in the R direction. Okay, so this is what you have. Here I have not shown the D7 branes that we also do not mess the thing too much. But what is happening at the level of the D7 branes in the R direction is that you have the NS5s, you are introducing the D7 different intervals. This is how you are gluing your solutions. And this, with the brane creation effect, is creating this D5 prime brane, which are the ones that form the bound state here with the NS5 prime branes. The prime, because they form bound state with that of Neveswar's 5 branes. And this is changing because due to the Hanani-Witten brane creation effect, one cross another NS5 with the 7 branes, this will change. So orientation between the bound states and the NS5' brains will orientate across intervals that I'm not showing. And the numbers of the D3 brains of these plaquettes is also changing as we move in the intervals. And this is a consequence of what I was saying at the beginning, that age data, the first derivative and the second derivative, they need to be continuous because they are metric, and this imposes conditions on the way the parameters that I was showing. This I forgot to say. The parameters in terms of which the H function is defined, when you impose that H prime and H double prime are continuous as we move in these intervals, how these charges have to be changing across intervals. Okay? And therefore, once we make the translation from charges to actual field theory charges, taking into account the higher curvature terms, this will impose how the numbers of brains in all these configurations is as we move in R. Okay, so this is the section is a complicated one, a brain box model, and they preserve 0-3 supersymmetry, and much is known about 2D 0-3 gauge theories. But, luckily, as it happens in ABJM, you expect that the field content is going to be the same as for 0-4 gauge theories, except for the deformations introduced by the rotations of the brains. And there's some multiplets massive. So what we can do is, okay, let's treat this as if it was 0-4 supersymmetric, ignoring for the moment the rotations, and see what kind of information we can get from this. And luckily, brain boxes with 0-4 supersymmetries were studied by Hanani and in quite some detail, and this is something that we borrow. So, in order to understand what is the field theory that lives in these brain intersections, you have to look at the position of the open strings that you have with both ends in the same stack of D3 brains to start with, imposing the boundary conditions that the two families of NS5 brains impose. This gives the content of a 0-4 vector multiplet that I will denote with a circle. Then look at the quantization of the open strings that connect D3 brains between some NS5 brains in the adjacent intervals. This will give you the content of a 0-4 hypermultiplet that just contains scalars. This can be of two types, or twisted, because you have for this symmetry is SO4, the asymmetry group, which is SU2 cross SU2. Under which of the two SU2s the scalars are charged, you will call it or not. And you can also have just a fermion, a left-moving fermion. This happens when you look at the quantization of the open strings that connect D3 brains across both NS5 and prime brains. It seems like this shouldn't be here, but in fact this is not a problem because this is a left-moving fermion and supersymmetry is realized in the right-moving sector. But this has a role, an important role when you construct potential. So these fields are really important to construct this. So with these elements, we are able to then show the quiver that is associated to this complicated process. Of course, it's a complicated quiver in which if you just, this would be again the R direction. If you just freeze R and look at this looks very similar to the quiver that describes ABJ. You have two gauge nodes wings that are N or N plus M. They are connected, in this case, this is two-dimensional, by two 0-4 hypermultiplets. Here with 7 brains because we are in the massive case, and the level that we had before in ABJM for the Chen-Simons action is now a flavor group because we have dimensions. We also have these NS5 brains that in the mass didn't have. So this implies that you have a collection of these quivers being repeated in a direction. Okay, and they are conveniently connected by the relevant fields that make this consistent in the I will now mention. So this was one of the examples I was showing in the introduction, in which you can see how you are inserting, in this case, NS5 branes. This is what makes that this is not just frozen in R. You have 9 and the D7 branes, which are these new flavor groups that you have here in the otherwise quiver describing the ABJM theory. And also have this difference coming from these flavor groups that cannot now Chern-Simons levels. So I said this is consistent in the sense that if you are building a 0,4 quiver, you have out-Gates anomaly, and this is consistently satisfied up to some caveats, because of course we are with our charges. I mean the ones that determine the values that you have on the background, that is 0,6 supersymmetric, so at the level of the brane intersection, you should not have Gates anomaly cancellation for 0,4 theories. And indeed, this is not realized, but it is realized once you remove exactly those massless fields that would be removed in the rotation of the branes. So in this sense, this is consistent. This is a bit technical, sorry, and I can explain to any of you better if you would like to. So here it is interesting. I was saying that there is a relation between quantized charges that you compute from the solution and the actual number of branes. When there are D8 branes, the relations before get modified. And when you take into account these modifications and you see how the charges are changing across intervals imposed by the continuity function H and its derivatives, when you translate that into this K, you find that this is the way they change across intervals. And this rings a bell, because this is no other than the realization of cyber duality J in the case in which you have a non-vanishing mass. This was proposed by Berman and Lipschitz in a non-supersymmetric setting, because they introduced the D8 branes in a way in which the whole intersection was non-supersymmetric. The D8 branes were treated as probe branes. Still doing Hanani-Witten moves, they proposed this Chern-Simons matter theory, which is in this way, and these ranks would be related in the IR to this other Chern-Simons matter theory. And this is exactly what we are predicting with this change in the charges across intervals. So what we are finding is a realization of cyber duality large Gates transformation. You know that in other theories, for the n equal to supersymmetry, in other theories you can realize cyber duality as a large transformation. And I mean, large Gates transformation is what I mean. Realize it as in terms of Hanani-Witten moves in a Hanani-Witten brane setups. We are doing this here, but in one dimension less. Interpretation is that when the D8 branes are embedded in the theory in a supersymmetric way, as we have done, which implies NS5 branes, then one of the 3D field theory directions, using field theory language, turns into an energy scale and generates towards a two-dimensional CFT. Geometrically, the background of these branes that we are introducing, the D8 and the NS5 branes, give to a 0,6 supersymmetric geometry, which is this ADS3 that we have analyzed, in which this direction become now part of the internal space. And now, in this geometric setting, is where we want to realize cyber duality in terms of large Gates transformation. So another thing that is interesting from this analysis is that using the Brown-Enno formula, you have a very neat prediction for the central charge that your 0,3 dimensional theory should match the holographic limit. And this, since these theories have not been constructed, well, it is a way to check what whether they satisfy these conditions. Should be an interesting thing to look at. Now I have like 2 minutes, so just mention very briefly that there is another class of solutions. This we had constructed not looking for defects, but classifying ADS3 spaces some years ago. These are solutions which are 3 crosses 3 crosses 2, foliated on a 2D surface with 0,4 supersymmetry, in particular symmetry. And these are solutions that already looking at them, you see the ADS3 part, the S3, this is a non-compact direction X, this is another non-compact direction Z, and S2. You see that here, this X to infinity, those of you familiar with the ADS7 solutions that Tomasiello and collaborators constructed to massive type 2A supergravity, you will see that the internal part is exactly what they have in terms of this function alpha, which is a function of Z, and it becomes asymptotically ADS7, parametrized in terms of S3 cross S3 cross interval. So this is a nice example of solutions asymptotically, as I was saying, to a higher dimensional ADS space. We try to interpret them in terms of D2, D4 defects in the field theory that lives in the brane intersection that underlies the Tomasiello solutions, which is NS5, D6, and D8. Because indeed, this is the collection of branes that we have associated to these solutions. We have the fluxes for all of them. So, indeed, the Hanani-Witten brane setup is the naive one I was proposing before, taking into account the effect of the CP3. Here you can construct another example in which you see that introducing the D2 branes and the branes gives you a consistent 0,4 dimensional field theory. These are the D8 branes, which can be seen as you are inserting D2 branes and you are inserting D4 branes that describes the Tomasiello solutions, which in this case is described 6-dimensional fields. These are the D6 branes, which in that case are the color branes, and the D8 branes. So this is, but when we try to compute the actual contribution of the defect degrees of freedom, for instance, to the central charge, we found, here I'm going to be fast, they were not contributing anything. So we the defects, I mean, what you do is you subtract the central charge of your 2D theory and the central charge of the mother theory. So to look at other configurations, we looked at the baryon vertex, we looked at giant gravitons, and compare those configurations in the defect theory and in the and here I'm not going to give any details. Baryon vertex, this was the introduction just to recall what this is. But first we had to construct the baryon vertex in the 6D theory, since different gauge groups, because you have river constructions. Well, there are different baryon vertices along the that are D2s, but well, you can compute by looking at the action of the D2 vertex and the fundamental strings attached, which is the endpoints around the quarks in the boundary theory. Well, you minimize, you compute the size of the configuration, and it turns out that when you do the same for the 2D theory, in the color branes are D2 branes, the vertices are D6 branes, you find exactly the same size and energy through some kind of miraculous cancellation in the calculation. This was quite surprising to see. So then we decided that, in fact, the solutions were actually described XT 1,0 CFTs, but deconstructed in terms of 2-dimensional 0,4 degrees of freedom. And the quivers that I showed were an expectation of this. So now I conclude very fast. I have -1. So just we focused on these two specific classes of solutions, numbers of supersymmetries. One of them we could interpret as defect within the ABJM theory. We could realize cyberduality in this way. And the other ones, well, we try to interpret in terms of impact. In the end, we end up proposing an interpretation in constructed 6D 1,0 theories. And this, of course, thank you very much.
Thank you, Yolanda, for the nice talk. The question?
I wanted to ask clarification about the ADS3. What exactly does it mean from the point of view of the field theory? Like you have a two-dimensional defect. How do you plot to a local two-dimensional defect? Is it because it's a slab or what?
No, I was using field theory language, but in fact the description that we have is purely geometric. We don't know exactly what is happening at the level of the field theory.
But this quiver you had, it describes what lives just on the defect.
This describes the whole theory with defect and mother brains. Yes. This is the whole theory, including the defects.
It remains conformal. It's still a VJA. It's still a conformal theory. The part
itself is a conformal field theory.
okay.
I mean, but it's, you can remove that part because then you don't find a conformal field theory removing the brains that come from your bulk theory. Yeah, okay. This is what we are trying to do now. I mean, we started doing this baryon vertex, giant gravity, but we are yeah. There are many other things that you can compute to verify what are these defects, but. Yeah, indeed. Something we have not done yet.
More questions? I have one. Probably it's a bit general. If you take the plane wave or BMN type of limit in this theory, do you think the defects survive or washed out completely? Have you checked it, or do you know if in some other context defects survive BNM type limits, Penrose limits?
We haven't tried, but I mean, you would be working with dimensional AES that is already taking into account that you have. So I would guess that by construction, you would be capturing the defects doing that. That could be interesting to also what's happening compared to whether you just take the BMN without the defects.
Okay. Perhaps later because we're out of time. Thank you, Yolanda.
Yeah, sorry for going over time.
Okay, the next speaker is Roman Yannick, who's going to years actually, talking about the Ising model as a window on quantum gravity in matter.
Okay, thank you very much. So first of all, I'd like organizers for the kind invitation. It's a great pleasure to be in Athens, first time for physics, in fact. But I've been here before, enjoying that beautiful town. So I would like to describe some recent work which appeared last February about, in fact, using trying to look at the model and trying to see some traces of gravity and black holes in the. So the plan of my talk is as follows. First, I'll give some motivation part of the motivation is obvious because it would be really fun to see black holes in the Ising model. And in a way, it's also, this talk is complementary to Alejandra because the Ising model is as far away from C going to infinity limit as possible. So basically, therefore, it's quite interesting, but also one can expect some hardware and some difficulties that we can encounter. But here I will also describe some motivation for the concrete setup that we use, because of course if we just go full force to the Ising model without any additional constructions, assumptions, of course it's not clear what's happening. So then I will give results of an Ising model computation of an observable, which is quite intriguing because part of the behavior is extremely natural from the point of view, but part of the behavior is completely unnatural. So kind of the main point of my talk is to try to understand this dichotomy, this kind of apparent contradiction in terms of a bulk description. So before that, of course, this is just purely in CFT. So it's not clear if there exists any kind of dual description for this model, which like for a minimum VSRO model. So I would like to very heuristic hand-waving arguments for a gravitational description, basically just a review of facts which are known, and then proceed to give the bulk interpretation of Ising model results and give a summary. Okay, so here we start from, of course, the AdS-CFT correspondence, which is the equivalence between QFT on the boundary with gravity. And typically, like if one studies non-equilibrium dynamics, one tries to look like equilibration and this type of stuff from gravity information on this field theory. But here we would like to the opposite direction, also in line with the topics of the workshop and with many other talks in this workshop. So we'd like to go here. Now, if we want here, we should really specify what do we really mean by gravity in such a. So here, if we want to use AdS correspondence as a definition of gravity, which is basically the main point, here it means basically that gravity is really the subsector of bulk theory, which is dual to the energy momentum tensor. And just to, of course, try to take this as a basic definition and extract all information from the field theory side. But one consequence of that is generally we are always dealing not with pure gravity, but always with matter, because matter will correspond to additional fields which are in addition to the energy momentum tensor. And AdS-CFT really provides us a quantum definition of gravity plus matter content. So it's far from obvious if indeed pure gravity is existent, and of course there have been works on problems with AdS-3 gravity, like starting with Witten and so on, of pure AdS-3 gravity. So here, like we would like to try just to extract properties of gravity from the correspondence, if they will be completely at odds with our usual assumptions about gravity. So, for example, we would like to, for example, restrict bulk topology to get rid of and so on. Try to keep a single QFT on the boundary, and then try to extract how far one can go to preserve holography, even if this is not what we would expect a priori of a theory of gravity. So we don't need this kind of an approach that we take. Why is it difficult? The problem is, of course, that we have to like two things. First, we need to have a good control of a boundary CFT in order to be able to do computations. But also we need some semi-characteristic regime for good interpretation. And usually, in most cases, we have or the other. But the problem is clear. Maybe that we are not really so interested in getting semi-classical gravity because we know what is gravity and more or less we know semi-classical gravity, but we would like to at least understand what is the bulk counterpart of what. For example, in N equal to 4 super mills, one can easily do perturbative computations at a number of colors, get some answers, but we will have no clue what they mean on the bulk side. So therefore, the main point here is really to have an interpretation, getting our results on the CFT side. So we specialize to 2D CFTs, and just what I said is that in a way it's complementary to Alejandra's talks, because here we are not assuming holographic CFTs, rather really in a deeply intermingled regime of quantum gravity and matter, if possible. So, and the claim which I will try to kind of argue is that we can get insight into some aspects of gravity and matter, even from the simplest Ising model CFT. So, right. But of course, we have to have something else instead of C going to infinity in order to have any kind of control of the bulk side, in principle. So, taking central charge to be very large, we consider first the high temperature limit, because we may expect that the temperatures in the CFT, things will be more or less classical. I mean, it will not be, not everything will be kind of semi-classical, but at least some observables which we can identify nicely. So in this way, we can hope to have some bulk understanding. No. Well, here I'm just. Yeah, but here I'm just. I will be keeping C fixed, going with temperature to infinity in this for this construction. And of course, not everything will be computable. Semi-classical. One will see in some corners that some parts would really require corrections. Right. Then we will stay on Minkowski side, so we will look at real-time dynamics. And we put the CFT on a special circle of certain size. So this is because if we would take the CFT on a line, then just symmetry would so constrain the theory that something non-trivial would appear on the level of 4-point correlation functions, of course. And this is quite difficult to interpret. While if we have a theory on a special at finite temperature, then even a 2-point function is non-universal and trivial space-time dependence. So therefore, and a 2-point function is much simpler to interpret than a 4-point function, because we can easily understand what it is. Now, now, what are the sources of quantum? So first of all, if we go back from the high temperature limit to finite T, we will see some kind of loop effects. So this is one possibility. And the source of quantumness in this talk is that since we have like a special circle, which is finite, this means that the CFT modes, of course, are quantized, which is kind of obvious. But now, if we go to the gravity side, the dual graviton should also be quantized, right? So one would have discrete energy levels for the graviton and the bulk fields. So we have an implication that if we look at evolution, real-time evolution for very long of the order of 1 over level spacing, this kind of quantization of the graviton and company would be relevant. And this is, in fact, I will show both of those effects will appear during in this talk later. Okay, so a theory at high temperature. How do we study it using holography? So first of all, we expect, of course, that it should be a quantum, like a black hole. And then, if yes, the most natural way to study the quantum hole is just to throw matter, throw some stuff inside into the black hole and see what is. Right. So basically, the first studies of non-equilibrium dynamics in N-equal for super Young mills were just a finite temperature black hole, and then looking at quasi-normal modes. So just throwing some matter, scalar fields, for example, and so on, and seeing what is the reaction. So basically, we try to understand not by itself intrinsically, but how it interacts with matter, feels gravity. In fact, this is the definition of like caves in this sense. Okay, so we will study here just linearized QN dynamics. So let's go to the CFT at non-zero temperature. So we'd like to do this type of story that we would like to perturb the thermal. So this means that we take the thermal density matrix and perturbation. And now we would like to make this small perturbation as natural as possible So we would construct it. So we take some primary field into CFT, integrate over space in a sense that we want to have zero momentum, so the simple situation. And then we model the thermal density matrix by just doing this type of similarity transformation. So at linearized order, we just have the commutator of rho and this integrated primary field. And then we like to study time evolution. We evolve it using the Hamiltonian of the CFT, and of course we will some observable. So the simplest observable is just to measure our original operator, how it behaves in time from this perturbation. So basically it's something like a 2-point thermal density function in real time, so something very simple. So we choose the operator to be here epsilon, energy density of the Ising model, so delta is equal to 1. This is very useful because then we will be able to very easily go from Euclidean to signature and to do the retarded computation. Okay, so what comes out from this observable? So now we do that model with this operator, and we can now time evolution. So first we see like an exponential behavior, which is like a quasi-normal mode regime. This is kind of universal, so it follows basically by conformal symmetry, and it's very useful. Now, then it turns out that this does not die to zero exponentially, but it saturates at some non-zero level of a plateau. And this plateau is already non-universal, so it details of the CFT in question. Then something strange happens at pi. There's some kind of strange burst appearing, but the most interesting feature appears at time equal to 2 pi. So then basically everything returns back to setup, and all information, all the signal is kind of appears again completely intact. Now now this part looks like a black hole, exponentially carrying something which is exponentially absorbed, and then some kind of hollow plateau creation seen on the outside in a way. But instead of having some complicated thermal absorbed and recovered information, what we see is that just the intact signal appears again without any change. So the key question is can we understand kind of both of those terms, those features, from a bulk black hole perspective, and in particular can we understand this emergence of this intact signal also in terms of some bulk language of black holes. So yeah, so I will show in a moment. Yeah. So here those curly lines are truncated conformal space approximations, so these are just numerics, so that we can test that we are doing right. Analytical result I will show, in fact, on the next slide. So in the Ising model, in fact, one can start from the Euclidean 2-point function on the torus, which was computed by Di Francesco, and then one can make an analytical to a retarded 2-point function. So basically at finite temperature. And now, because delta is equal to 1, this retarded integrated function can be computed by residues, which makes it much more easy to study. And if one just takes these formulas from Di Francesco, computes those residues, one gets this expression to be a ratio of those theta functions. So this was the curve, the red curve seen on the previous slide. So now we can look at this. And first, look in the large T limit when the time is 1. So it's this type of expression. So basically, this part is the feature, which gives rise to quasi-normal modes, easy like quasi-normal modes, just by symmetry. The plateaus here, and it is kind of exponentially suppressed at large temperatures. And now going to if we look at this exact expression, one can just see that this is exactly periodic from those theta. Well, so those ups and downs here, so like one should look here at the red curve, because those are truncated conformal space approximations, so these oscillations are kind of artifacts of truncating the Hilbert space for the time evolution. So now, this is just periodicity means that the signal emerges unchanged. The CFT perspective, it's something completely obvious, because here Lorentz spacing is 1, so evolution into evolution 2 pi should be periodic as far as descendants are concerned, and here moreover the Fune rules are such that this is exactly periodic. Yes, one can also get the burst. Yes. Mm-hmm. And for minimum models, in general, time evolution is always periodic, right? Because we have a number of rational dimensions. So looking at clearing the denominators, one will always have a period which is a multiple of 2 pi here. So therefore, this periodicity is a generic feature and always appears for any observable, whether it's thermal or non-thermal or anything else. So from CFT perspective, extremely general, but it's very surprising from the gravitational black hole perspective, in contrast to this QM-like behavior. But of course, we have to ask the question, is there anything on that side? So is it just a property of a CFT? Any gravitational picture? Do we expect to have any gravitation on the your side? Well, just here, just from the high temperature limit, I used, so one has to do modular. Yeah, but because when one continues to Minkowski signature, one has those theta functions with real arguments always, only appearing. So, so for physics, I don't know if what is the trace. Okay, so first, just a reminder. So everyone knows that about Chern-Simons gravity in 3 dimensions. So basically, we have 2 gauge fields, which are parameterized in terms of holomorphic functions, and the metric is obtained from both A and A bar using this. So here, I would just like to emphasize that this formula means that, in fact, the horizons and the causal structure is encoded only from both of the potentials. If we just take one of them and change, we can just like rotate a BTZ black hole, so completely change the horizon, right? So therefore, it's really crucial to have both of them. And second, in fact, from the Chern-Simons point of view, this is not a very natural expression, right? It does not, like in Chern-Simons, the metric is really not a fundamental concept, but it's a derived concept. So it's really clear whether matter fields will have to obey couple it to this particular expression, which is a bit strange, or they may just couple directly to the gauge fields of Chern-Simons. And this will be important in my talk later. Okay, so so now how to argue for holography for various minimum models? It's completely hand-waving and heuristics. So first, we have this Chern-Simons Westomy-Nowotny equivalence. So if we have Chern-Simons on the disk with group G, this is the same as the variation of Westomy-Nowotny CFT with group G for compact groups. If we have here matter representation, this representation is causing a puncture and adding a Wilson loop in the center of the disk. Now, if we specialize to SL2R, we would expect something similar for SL2R. It's non-compact, so there are lots of problems here, but suppose that it works. And then we'd like to impose asymptotically ADS boundary conditions. Now, this would mean, so asymptotically ADS boundary conditions here would correspond to is equal to 1, where J plus is one of the currents of SL2R. And now, once this is done, we can go back to a very old paper by Beshatsky and Oguri, who, for completely different reasons and different motivations, in fact, showed that one can impose it on the level of BRST cohomology and showed that the representations exactly coincide with the representations from minimal models, and also similar for the matter representations. So now going back, this suggests that there should be a description of Virasoro minimal models in terms of some quantum three-dimensional Chern-Simons with some Wilson line going back. Yes? So they have some, they derived it in this, I don't remember offhand, but in the this proof, so the proof algebraic, and yeah, yes, because definitely, yeah. So I don't remember the details. Yeah. Yes. No, here, like, I go with the hypothesis that, okay, I would say that three-dimensional Chern-Simons on the quantum level is a three-dimensional gravity theory. Also like Virasoro TQFT, right, and so on. So I'm not saying here anything unique 3D gravity. That it is a possibility in the sense that it is like Poincare gauge diffeomorphisms. Yeah. Mm-hmm. Okay, so now, like, if we want to speak about this holographic quantum Chern-Simons, what could it mean? So this one heuristic thing is that consider those SL2R gauge fields, in fact, as quantum operators which are defined in CFT directly. So one can write this type of expressions where now this is something, but now it's defined in terms of operators purely on the boundary. So this gives us like a realization of holography in some sense. Here one problem is that one has this coefficient here. So how to derive this coefficient, in fact, from Bershadsky-Oguri construction directly, probably because of quantum effects. So in this sense, this coefficient can be fixed. That expectation value of this operator in the vacuum should be ADS. That's the only way that I know to fix this coefficient. It's not really precise. Yes. 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 No, so I don't know how. It's a very interesting question how it works on the level of these expressions and so on. It's then non-trivial because if one would go to Eddington-Finkelstein, for example, something more complicated, and so it's really nice only for Graham. And yeah. But anyway, now use it as in the following way: that since these are operators in the CFT, we can take the thermal average of those operators, and then clearly one could get the answer here, which is Z independent, of course, and similar here. So in sense, we can expect that we can be dealing with a BTZ black hole even for the CFT at non-zero temperatures on the level of geometry. This also define also the metric in this sense, and a funny thing appears that the thermal average of the metric gets some kind of quantum throat correction, which kind of open up the horizon in some. But in fact, this does not seem to be relevant for anything which I will today, so I will not describe it in any more detail. Okay, so now we can go back to the to the Ising model and try to look how to reproduce those results from the CFT computer in terms of now this dual picture of those Chern-Simons gauge fields, which are sitting in at the BTZ black hole points. So the prescription, the general prescription, is in fact in terms of Wilson line networks, which are some parts of the exponential also similar with A bar, and some trivalent junctions which are associated with trivial OP coefficients. And here, those gauge fields with non-compact representations of SL2R. Here we have the energy momentum tensor, what I already said related to the OP coefficients. And one is to deform those contours in any continuous way due to topological theory. And one can see lines as a kind of first quantized red line picture of some topological matter coupled to. So this is the way that we will try to interpret. So I will not give any kind of space-time bulk interpretation of this matter fields, but just use the Wilson language. And of course, the computations of language are completely gauge invariant. So one can choose it's standard to choose a simple geometric gauge in some way. So we relate those Wilson lines at high temperatures just by exponentiating thermal. And now, therefore, this means that like the corrections will be like connected correlation functions of the energy momentum tensor. One knows that at large temperatures, this is in fact exponentially suppressed, unless the points are very close to each other. So this is like a justification a posteriori that gives kind of like C going to infinity limit, with caveat that for small separations there may be problems. So it's not completely controllable, but for those questions which I will address here, at least some can understand something. Okay, so get the Q&A regime. One just so this is just the circle cylinder. Here's a singularity, and it's consider such a simple Wilson line and outcome, which if one performs the computation, and A is just pi times. Now specializing to this case, we cover normal mode like behavior. So this is just nice because we expect the symmetry that one should get this type of 1/sinh behavior here, and it arises from this Wilson line computation. But now we can go over non-universal case, which is the plateau. So we call that the plateau means that this does not die off to 0, but the constant level, which is of the order of E2 over 2 times the temperature. So this is in fact reminiscent of a computation from by Krauss and Maloney, who looked at one-point function in terms of bulk scalar fields on a BTZ black hole background. And then they found a contribution which came from a scalar field which was wrapping around. And the magnitude of this wrapping of a scalar field among the horizon was this E2 minus 2 pi r plus delta horizon radius. And now the delta here is the field which is in the loop. So it's not this epsilon, but it's in fact sigma, which has 1/8. And if one plugs in delta equal to 1/8, one exactly gets pi squared over 2 times t. So therefore, it's unfortunately here in fact is one loop. Well, sorry, 1-point function gives the contribution, but for a 2-point function, a very similar structure appears from this Wilson line network because one has trivalent vertices, diffusion rules, and in fact, computing the contribution to Wilson lines here, which surround the singularity, one recovers E2 minus pi squared over 2 times t. So here we see that this plateau is also very natural from this gravitational black hole interpretation, and it's like a quantum matter effect because it involves a sigma loop. Okay, so now we can go to the most intriguing story here, which came from this periodicity. So what we should add to what we had up till now. So clearly we should add Wilson lines which have arbitrary winding numbers. We'll give just a sum of n to minus infinity to plus infinity. Here same formula as before, but z is shifted, the difference of z points is shifted by 2 pi n. Of course, we should not now incorporate anti-Coulomb because all those lines are charged both under H and A bar, with H and H bar. So therefore, those parts we will get this type of expression. And now, in fact, agrees with the scalar Green's function from planar BTZ black hole, the method of images, right? Because this is just like with a single grouping, it will be just the answer for infinite line, which is exactly that, and here to mirror images. However, this does not lead to recurrence at all. Stand with the fact that the scalar field, which we just put in a black hole, will just be absorbed and nothing will happen. So what happened? So here, for the Ising model, fortunately, we have the exact expression. Just look at those theta functions, in fact, for the Di Francesco result before residues. And it turns out that the structure also has building blocks at high temperatures. Those 1/sinh with some shifts. If we look closer at how the holomorphic and anti-holomorphic parts are put together, in fact, formations, each of those parts is individually periodic. So this is just a loose constraint that the parity of the winding is similar. So now we can use the fact that each of those factors, in fact, has a nice in terms of a Wilson line with appropriate number. So what this formula tells us is that we can exact CFT answer. What are the allowed windings of the holomorphic and anti-holomorphic lines? And now we can make a picture and see what is the difference between the previous slide and this slide. So in the previous slide, we had the Wilson line which had both charges and all those. So we always have like both holomorphic and anti-holomorphic Wilson lines on top of each other. While this, from here, is in fact that the windings are almost independent. The picture is such that like in the bulk, the holomorphic and the anti-holomorphic Wilson lines kind of live their own lives up to this small, some kind of topological constraint, which is very mild, that just the parity of the windings have the same. And CFT picks this instead of that, because we can read it from the Ising model. Okay, so what are the consequences for that? So first of all, we can go back to this interpretation that the Wilson line trajectories are like word line interpretation of quantum matter, right, of matter fields in the bulk. And now the fact that we have kind of independent holomorphic and anti-holomorphic Wilson lines seems to indicate that in the bulk, in the field, which will be a single one which is charged under both groups, in fact, a pair of fields, one interacting only with A and the other only interacting with A. And for all observables, so for boundary instances and also for the vertices in the bulk, those fields pairs, right? So the trivalent vertex is really a 6 appropriate pairs for each primary fields. But a part can just move independently. So this would seem like a curiosity and some strange feature. Go back to the fact that if you recall that the metric and horizons is only both through A and A bar, right? So therefore the causal structure is encoded only when we interact with both of the gauge fields. If a field interacts with only one of them, it can basically be part of the geometry somehow. And it kind of evades the black hole information paradox, because the metric is really not interact with the metric by itself on level. So the interaction of those fields somehow is a bit different. So the very surprising outcome is that here that gravity may not gravity at all. So it's not really working in terms directly of mentality, but in terms of those Chern-Simons gauge fields. Of course, this is dual gravity description of CFTs. However, it's quite mild because this effect only appears at non-zero winding. If we would have zero winding, we could of course move those things away from each other, and it would be exactly the same expression as they go together, right? So therefore, as far as the topology of the space-time trivial, like on the plane or at 0 temperature, this would not be seen. For small times, also everything just behaves as a scalar field. Quasi-normal mode decay, and then we have this plateau of a loop going around the horizon. Okay, so now summarize. So it seems that I try to argue that the Ising model can be used to study quantum gravity with matter in some way. So one can really focus on some and see some strange behavior. So this is the Béchatski-Ogury construction. Also, it would be very nice to really get those steps in this heuristic approach and really make them precise. Because, for example, non-compact Chern-Simons Wess-Newton on the quantum level, about the central charge, the 6/c coefficient here from this Béchatski-Ogury construction. There's some, for example, ghosts which are involved in these BRC constructions of Béchatski-Ogury, which are not present on the normal particular ADS conditions. So all these type of questions will be very nice to address. So we probe here, so we study this high temperature limit, we probe the black hole in matter. We have this dichotomy that quasi-normal have very natural black hole interpretation, but its recurrence periodicity is extremely from the black hole perspective. So the kind of the outcome is that somehow the gravity here does not really behave like our expectations of gravity. That somehow the metric is not really a fundamental concept, Chern-Simons gravity, and because of that, matter fields can in principle couple differently to Chern-Simons gravity than we would expect by coupling only through the metric. So, and like the surprise is that the CFT dynamics seems to really point us that indeed the bulk matter does not couple as to the matter, so this very strange individual coupling to A and B. And in this way, it kind of evades the black hole information paradox because it reappears completely unchanged. So there are lots of open questions. For example, one can go to further. Otherwise, there are more like richer set of fields. Also, we are looking now at Baking conformality. Also, that is possibility is going to high dimensionality. For example, if one would look at n equal to 4 Park Mills on a sphere with fixed radius and go to weak coupling, then it also has periodicity. Definitely periodicity in that n equal to 4 Park Mills can low coupling in the free theory also exists. And of course, there are lots of theoretical questions like exact proofs. What is the space-time interpretation? Is it possible to really use this language to really computation exactly and thus be able to prove all those formulas? It's also very technical and difficult because then one would really need to consider all connections between the energy amount of tensors on those different lines of the Wilson network. Okay, thank you. Well, I would say that like here, one really got the high temperature limit of the full CFT answer on the torus. Well, I would say like so they consider just say putting it on a cylinder, right? So therefore they consider the pattern functions. So in a sense that what the character of the Virasoro minimum model is exactly matches to the Wess-Newton, which is J plus equal to 1, the matter field, right? And then if one would have Z and a Wilson line in the center of the cylinder, one would get a complete match. And I think, and so I would say that here we have to put in by hand what matter fields are present, right? Because they do not. It would be very nice to find an action which would predict for us what a matter field, but perhaps it's too much to hope for because even minimum models do not have really kind of formulation. So here we have to specify those. Yes. What kind of lines are allowed and what kind of vertices are allowed? We have to put in some way. Yes.
Where exactly the information that the gauge should be?
No, so here in the Beshatsky algorithm, it just comes from that link. That to get the they made an also in that paper they made a generalization that for I think for WN they have SLN. So it also appears if one has higher, but for just minimum models of the Virasoro, one has SL2. So SL2 Kac-Moody. So this will go over to Chern-Simons SL2. Yes, so in fact, so the burst, if one would trace back, yes, so in fact, the burst would come from this diagram, like that. But here the problem is that if one bring those, but to get the burst, one has to bring those two legs close together. And therefore one would need to have contractions between those two lines. So definitely those quantum contractions would be needed. But if one would, but one thing perhaps I would add is that one can match, expression should be matched in principle to a certain 2-point conformal block on the torus with the A cycle chosen in some way. And one knows what is this of the sigmas. And then one can just read off that from the exact expression and also the burst. One can also derive the burst from this expression which involves the sigmas. So this is the effect coming from the sigma loop, but involves putting those two points close to each other. And therefore this will kill, unfortunately here the high temperature will not suppress corrections, so this will have to be resummed. I don't know how to do it. So it's a very interesting problem to really this coefficient here and get the burst from such.
No more questions?
So please take a seat. Let's continue on with Sam Gulam, who's going to talk about negative specific from gauged matrix and tensor quantum harmonic oscillators. Please.
Great. Thank you very much to the organizers and to the participants for being here. So yes, I'll be talking about negative capacities from gauged matrix and tensor oscillators. This is work done with with Denjo O'Connor over the last year or so, where we talked about basically gauging finite group symmetries, where you have your matter degrees of freedom being matrix degrees of freedom, and then setting up path integrals, calculating explicit partition functions, and then extracting some physics, and then finding that these naturally give rise to negative specific heat capacities. We first found this phenomenon in this finite group symmetry setup, but they also exist in continuity setups. So the examples I'll talk about will include both of them. So just to get started, matrix quantum mechanics models have very interesting thermodynamics, which have been interpreted in the ADS correspondence. And the mathematics behind the counting of polynomial functions of matrices, variables, or tensor variables. And we're looking at polynomial functions invariant in the appropriate symmetry group. And so within this world, it is there are very natural occurrences of the heat capacities, and some of these examples may well be of interest with small black holes in ADS-CFT. So to show you some of the simplest examples of the counting and build up from the counting of states in the simple examples to the more complicated examples, and see how the partition functions change. I'll just remind you of the basic examples of L equals 4 super Yang-Mills, where you have 6 Hermitian matrices. You take a pair of them, form a complex combination, get a complex matrix, and look at polynomial functions of that. Essentially traces powers of traces of powers and multiple, so multi-trace operators. These are the kinds of things that are very interesting in T. And CFT gives us an inner product on this space of states. And the free field inner product is very important in the half PPS sector because it's not renormalized and it contains a lot of physics of the strong coupling limit. Now, this free field inner product can be also captured purely in quantum mechanics. So you can just have a quantum mechanical model with quadratic potential, and the same inner product arises from this very simple setup because it's a complex matrix. You have 2 oscillators, A dagger and B dagger, and the kind of half BPS sector of holomorphic matrices corresponds, holomorphic functions corresponds to taking just essentially states related to one of these oscillators. So counting of such things, you just simply count multi-traces of one matrix. So if you have total energy 3, you can have a single trace, or 2 traces, or 3 traces, depending on how you distribute your 3 oscillators in among these traces. So 3 equals 3 here, 3 equals 2 plus 1, and 1 plus 1 plus 1. So these are partitions of the number of the energy that you have. So counting is simply counting of partitions. Now, very interesting thing about that, well, already you see that there's an important qualification, is that if it's a 1-by-1 matrix, then it's a dagger 1, 1 to the 3rd power, and all 3 are actually the same. So the counting, there's a generic counting that holds when the matrix size is large enough, as the matrix is bigger than 3, this is the counting. But when the matrix size is smaller than the energy you're thinking about, the important qualitative changes. So basically, here we are. The counting is given by the partitions of K. K is the energy. And this is independent of N as long as N is bigger than K. But the counting is changes when the number of size of the matrix is less than K. So there's a full range which goes like counting of partitions, the asymptotics of that like e to the root K, and then this. So this is quite generic in all the countings that we're going to talk about. There'll be a stable, and there are some well-defined corrections when you have finite n effects. And these different kinds of, there'll be different kinds of large K asymptotics, which will lead to different kinds of thermodynamic behavior, finite temperature Hagedorn transitions, or zero temperature, and in some cases negative specific heats, which will be, a lot of that can be sort of guessed by knowing the right form of the large K asymptotic in the stable regime. So the next example involves two matrices. If you have, for example, the new thing now is that the order within a trace is important, and that a great increase in multiplicity. So rather than e to the root partitions, we get something much bigger. We get growth of the counting of states like e to the k now, not e to the root k, but e to the exponent. So now if you look at the thermal function, e to the minus beta k, k is the energy, this is the degeneracy. Now, depending on whether beta is smaller, this will converge or diverge. And as a result, there is this Hagedorn transition. So for T, small temperature, large beta, this dominates, this converges, all good. But then you have this Hagedorn transition, at which point this term starts dominating the negative. So this is the confinement transition that has been discussed. So this, just the free counting shows a very interesting feature of transition. Now, just a little bit this finite group stuff. Well, one of the kind of applications of matrix models beyond quantum mechanics and so on, pure statistics. So you can use matrix models to write down some probability distribution over the space of matrices, and these have been used to analyze statistics of real-world matrix data. Work of Wigner and Dyson, energy levels of nuclei, energy, space level repulsion, and so on, come from very simple things like this. Have been applied in other areas of physics as well. So things you might ask is, what if I kind of start this kind of invariant under ON or UN, depending on whether you think of matrices or Hermitian matrices or just real matrices. In any case, this same kind of under continuous symmetries. But what if you replace these continuous symmetries by discrete symmetry? What happens to these actions? And in particular, let's say we want to look at Gaussian actions, which means at most quadratic terms, linear terms, and quadratic terms. And now, instead of having a symmetry, let's say M goes to UM dagger or UM U transpose for all ON or UN matrices, you just restrict the invariance to be the U is a gauge symmetry now that you're going to impose U simply in Sn. So what happens then? Counting of the invariance, instead of counting traces, you're counting something very simple still. At linear order, so the permutations will act both the left index and the right index at the same time. So if you well, this is the trace, it's invariant under UN, ON, OSN. You have something like a sum of ij, mij, because the permutations act on these indices, and you're summing these indices. Therefore, this is also invariant. So you get two invariants rather than one at linear order. And for quadratic terms, you get more. There are 11 invariants, and there's a very nice counting of these invariants in terms of graph. So you have, for example, some of the usual Mij, Mji, trace-like things. But you can also have something like this, sum of J, MKL, just the sum of all the indices, and the graph theory interpretation has to do with associating an index to node and a matrix to a directed edge. That's
anyway, counting of these invariant functions is associated with counting of graphs. So these kind of Gaussian models have been studied and applied to real-world data in some sequence of papers, and that sort of brought us into
permutation invariant model.
now. Most important, an important point here is that this counting, as I said, graphs, and it grows very rapidly. 2 at linear order, 11 at quadratic, 52 to 961. It's growing faster than the counting of partitions. Then we started bringing this kind of counting and sort of exploring of this state counting in quantum mechanics. Now you have a matrix X, n by n matrix. You try to count the thermal partition function, and you want to really make sense of gauging the SN symmetry, and you can write down partition functions and path integrals that will do this. The trick is that you, the thermal partition function of this thermal circle,
Thank you. You can discretize it, and then you can make sense of what gauging that symmetry means, because now when you things, you have a transport operator and there's a group element that's in a finite group easy to make sense of, whereas the connection is harder to make sense of. So this kind of work was done by Denjo, O'Connor, and collaborators for the case of continuous symmetries even before, but adapted to discrete symmetries. And then you can start from the path integral formula and get some nice answers for what the counting is. So for example, counting the thermal partition function reproduces a nice Mollien-Weil formula for the counting of invariants, which is given in terms of a determinant. That connects with the physical idea of gauging this symmetry. So that's your motivation for studying what these partition functions look like. So in the next, we'll talk about these partition functions in the SN case, talk about the thermodynamics in the canonical and the microcanonical ensemble, and how negative specific heat capacity arises, and other things I'll develop depending on time. So, great. So we have the counting of states. We have matrix, a single matrix. First, now forget about the gauging. So if you just count this simple harmonic oscillator, just the n square oscillators. So you're just counting. This is the energy will just be the number of oscillators. You can build the minus beta E times the degeneracies. While at leading order is ground state, there's n square oscillators, and at quadratic order you symmetrize these n square things, so you get this number, and that's what you're going to do to get the and that has a counting function, or a function of e to the minus beta written as x, has this very simple form, and that's simply the trace of e to the minus beta of the Hamiltonian space, which is spanned by these oscillators. When you do the SN gauge theory, what you're counting now is simply the SN invariant thing. So there's a projector which acts in some appropriate way on this Hilbert space, and you have to insert that projector and do this counting. And so the Hilbert space at k level is some k oscillator Hilbert space, e to the minus beta k, and you have to projector. So that's just what this is saying. Now, what exactly is that Hilbert space of k oscillators? Well, it's actually the symmetrized tensor product of taking the A dagger ij, that's the Vn transform, and tensor, and the natural representation of Sn with itself. And then you have k copies of that because they're k oscillators. But then there's a symmetrizer because they're bosonic. So there's a projector for that symmetrization in Hilbert space itself. So at the end of the day, you can write this partition function in terms of, at fixed energy, in terms of something very simple, tracing is just the ordinary tensor product space with a projector for symmetric Sk and a projector for Sn. This is for the bosonic symmetry, this is for the gauge symmetry that you're introducing, and that can be calculated. So it can be calculated in summations of N and K, and for the gauge symmetry, K for the bosonic nature, symmetry factors associated with the partitions. There's some of N, partitions of K, symmetry factors, and there's a nice sort of coupling between the two partitions. You have a product from I equals 1 to K, and you have a sum over, so these I's represent cycle lengths for this Sk partition, and then there's a condition that L, which represents cycle length for the Sn, that length has to divide the cycle length for the Sk. So you're summing over divisors, and then so there's kind of a nice formula that's quite concrete. And it was kind of worked out in the context of these data science motivations. And this formula has this nice stability property that when the energy is less than K, you have some universal form, and then there are more complicated things going on when the size of the matrix becomes small. Now, so to do the thermodynamics as a function of temperature, you want to get a nice formula as a function of x, which is the temperature, or e to the minus beta. To do this whole sum over all energies, and then that can be done, so that sum over partitions of Q now disappears because we want to sum over energy, so multiply this by x to the k, sum over all k. So we have to do this sum, and that again takes a very nice form. It involves integers, LCMs, least common multiples of them, the GCD, and so on. So one can get a very nice sort of form which can be obtained either from this projector stuff or from the Moulin-Weil formula, determinant formula that comes from the path integral, and then you work out in detail what it means for Sn. You get this. So we get this formula, you know, for finite temperature, and coefficients of this, the numbers at each energy. So great. So now we can see the dynamics of this. So we know the partition function, take the derivative with the inverse temperature, get the expectation value of the energy. It's convenient to divide by n squared. That'll be the energy per particle in this n square system, n square matrix oscillators. And these quantities have nice large n sort of behaviors. And you just plot the energy as a function of temperature, and you see as a sharp transition at some temperature, finite, for fixed n. And then as n increases, you still have a sharp transition, but that transition go and lower temperature. You can work out the specific heat capacity. There's a peak where that jump was, and again that peak recedes to lower and lower temperature as n increases. And that is sort of expected, because what will happen in the infinite n limit is that this transition, this peak will become higher and higher, and this will go to 0. And this is sort of something we expect, because as n goes to infinity, we are in the stable limit, where the counting is basically the counting of graphs that doesn't know about these finite n effects, just like the counters. So there was counting of traces led to e to the root k, counting of these graphs leads to something like k factorial now, so much bigger than e to the root k. So e to the k log k. Now this, for any finite temperature, any finite beta, for large k, this always dominates. So this will never converge. If you first take the large n limit and then do this, you diverge at any temperature, no matter how small. So at large n, so now we're doing finite n and taking n to infinity, expect this sort of feature to reach 0. I guess just by looking at the stable sequence. So kind of 0, what was called 0 temperature Hagedorn, was observed in the context of tensor models. It was recognized very high growth, very big degeneracies are associated with like something like a zero temperature Hagedorn transition. So here we have explicit formulas for the finite n story, so we can approach that very explicitly. So now we can do this in the microcontroller. Here you look at the degeneracy as a function of n and k. There's an entropy. You can get the inverse temperature by taking a derivative of the entropy with respect to, and entropy is now in the stable limit log k. And when you take a derivative, the k1 derivative, which gives a log k, take a derivative of log k, you get a 1. So 1 plus log k. Important thing, T inverse is increasing as k is increasing. So temperature is decreasing, is increasing. So it just simply follows from this k factorial behavior. They're going to get something where I've plotted energy versus temperature here. And this is the stable region where finite energy is kicked in. And you're seeing this negative specific heat as temperature is increasing, energy is decreasing. And then at some point, these effects control these very rapid growth states. And then you just get a turnaround from negative specific heat to specific heat, and this starts behaving like n-square harmonic oscillators. And at high temperature, the gauging doesn't matter. And you get very similar to harmonic oscillators. But this kind of counting, there'll be a very large region, and much bigger. This transition happens at order n log n, energy order log n. So as n goes to infinity, this will become very large, and there'll be a big region of negative specific heat capacity. So, and there's also a form, yes, so that's the n log n that we've got numerically by fitting where that turnaround happens. Now, so I mean, it is a feature of the finite n or large n. In the large n limit, let me get. So you might ask, but we've heard we shouldn't have negative specific heat in simple systems. Well, in the canonical ensemble, you won't have this negative specific heat. So because there's a very simple calculation here. So large n is like infinite volume, and so but then from the sort of thermodynamics, maybe you should look at energy per particle, which is what we're looking at, and then so there will be a sense in which canonical and microcanonical agree in the large n. Maybe I'll tell you about that in a second. So canonical ensemble, the specific heat derivative, you can work at the dispersion of the energy, and it's always positive. So basically, if you plot that energy versus temperature in canonical ensemble, in the place where, in the region where you're getting negative things, that's around where you're getting this transition. But this slope is positive, so that's the canonical one, and that's a microcanonical one. And once you go beyond the transition, they will agree. And then if you think carefully about scaling the and taking the large n limit, then, as I said, this will go to 0. I said this was n log n over 2, but when you take the energy per particle, it'll be log n over n. So this will decrease down to 0. Somehow all this funniness will happen at 0. But, depending on what kind of physics you're looking for, small black hole or whatever, that this is an important branch. Very, very similar curves happen for small areas. So we actually have an analytical, well, yeah, we do have an analytical argument. it because this comes from the k log k, okay, factorial growth, and this high temperature behavior can be from the path integral itself. Oh, the location. So actually, we don't have an analytical argument for this n log n, but we do have an analytical argument for where this transition happens. I'll tell you about it shortly. And I think this is a bit correlated, these two things. Yeah. So indeed, so this canonical ensemble, that we can get an analytical argument for. So this partition function, was a sum over this Sn functions was a sum over partitions of something that depends on partition. And the form of that, there are different powers of 1 over 1 minus x. So I gave you this formula before. So the powers of 1 minus x in various places here. And if you pull out the power of 1 over 1 minus x, that power is something which we call the degree that depends on n and depends on the partition. And then there's something which is regular as x goes to 1. So the power of 1 minus x, again, it's a sum over the parts of the partition I length, so cycle lengths, if you like, density square, and then the GCD divisor of the pairs of cycle lengths and so on. There's a formula here which tells you how much what power they contribute. From this formula, you can prove most singular terms come from simply the partition corresponding to the identity partition, and the second most singular comes from when the cycles in the permutation are length 1. There's a single cycle of length 2. Somehow, being term in this high temperature limit come from small cycles. And so this is high temperature because x goes to 1 is that goes to 0, 1 over t. So 1 over t goes to 0, t goes to infinity. So high temperature is essentially a high temperature expansion. You can look at the first two terms and you can say, where does the second term start becoming comparable to that? So when does it become a, some small number a, or the 1 number? Let's say 100th of that. And you can solve for what x will do that, and you get n over 2n plus some 1 over n corrections. So that gives you an estimate for where the high temperature expansion will break down, and the high temperature lead temperature is just doing that. Where does it start breaking down? It's an estimate for where this is happening. So that's at log n over 2n. And indeed, as n goes to infinity, that's going to 0, which is 0 temperature. So yeah, so we do have an analytic formula for that. It would be nice to get analytic formula for the energy itself. Maybe there's something to do to, hopefully that should be doable. We can also look at the specific heat capacity as a function. And what is the peak of the specific heat capacity? At the point, it seems to behave like n log n. This is numerical. So it would be nice to understand these features a bit more, kind of build a model for what's happening at that transition. So to summarize, when we look at the UN symmetry, we had e to the root k growth when to infinity. We had e to the k log 2 for the 2 matrix case, finite temperature. Here we got 1 matrix but discrete symmetry, e to the k log k, with a 0 temperature Hagedorn transition. So then look at different types of growth and say, okay, when can I get this negative specific heat capacity? Essentially, second derivative of the entropy is what is important, and you can get super exponential growths that do that, like this k log k, or small variations of it. But you also find that there's a sub-exponential growth that can also do it, e to the k log d, or k times this is exponential. But then if you correct this k by logarithmic terms, then it turns out that if a is negative, so that will be slightly sub-exponential, that will also produce negative specific heat just by taking the derivatives. So something like near exponential, but sub-exponential. So that can also do that. So there are similar systems where these behaviors, these other behaviors happen. If you take an extensor and you impose, let's say you have a complex tensor forming in the tensor product of fundamental representations and its conjugate in the conjugate representation, and that produces a counting of invariant quantum states where, again, you have oscillators with these holomorphic or fundamental indices, anti-fundamental indices, invariant things look like that, the first with the first, second with the second, third with the third. But you can also have polynomials in A dagger, polynomials in B dagger, and you have to construct like the first index in all possible ways. There's some permutation that will do that. First index contraction, second index contraction, coming from a triple of permutations. And then there's some kind of bosonic symmetry. Well, there's a bosonic symmetry of these things, which leads to some equivalences. And there's a nice formula for the counting as a function of the size. These indices, I goes from 1 to n. If you're looking at states with energy little n, there's a counting of this, counting, where you sum over triples of Young diagrams with little n boxes, and the lengths, the heights of these Young diagrams are no bigger, capital N, and this is the number of invariants, number of one representations in R tensor S tensor T, which is the Kronecker coefficient. So a formula, group theory formula for this. There's a large n asymptotic as well, which is n factorial, and this asymptotic estimate is what, again, n factorial, or k factorial in what I said before, my notation before. Again, k log k type behavior. So again, this has this negative specific heat, which is again controlled by the finite n effects, and which the structure can be worked out from the path integral. So you use high temperature behavior, and then for low values of capital N, you can plot the data, you can see how there's this negative slope, and it just starts down. Things become harder to compute as the energy becomes high and capital N becomes high, because this form is too easy. I mean, you can code it, but not too easy to get numbers, let's say for n equals 30, for any energy equals 40. It's not easy to do this. In the SN case, we had this explicit product canonical. It was easier to work with that. But anyway, there's enough to get some evidence of this turnaround. And then the next, so can you do this in all models? So you can, so you complex matrix model, just UN transformations, and let's introduce another U1. So let's say Z is going to be charge 1, Z dagger is charge -1. We're going to now start looking at gauge invariant functions of Z dagger. So traces involving Z and Z dagger. So it's essentially a two-matrix. But we know two-matrix problem leads to e to the. But if you put the condition that the number of Z's is equal to the number of Z dagger, so neutral under this U1, there's a reduced counting. And the looks like as a function of energy and little n, but it's corrected by 1 over root n. So it's precisely the kind of correction that leads to negative specific heat. So we have plotted for n equals 13 of a few sort of points that will, there are just only 3 or 4 points like this, but then this chaotic behavior takes over, and then you get this lunge, and then at high enough energy it starts turning around. So if we start doing this with higher n, there will be just a few points, and then this branch will start becoming longer, because this operates whenever capital N is much bigger than energy. So capital N becomes much larger, you have a bigger range where the stable regime works, and you get negative things, and then at high temperature you can work out from the path integral it should become. So you see the same feature in this case. And this plot was obtained again by some group theoretic formulas. So let me just see how much time I have. 10 minutes. Okay, so and to rush too much. So to summarize then, there are 3 different examples where we saw very similar features. The one matrix discrete symmetry, there was this k or k factorial growth when capital N is much larger than k, and then in the 3 index UN tensor 3, there was again either k log k, so very similar, 0 temperature Hagedorn, negative specific heat capacity, and then there was here 2 matrix case with UN, where we had a growth of e to the k log 2, but corrected by root k. And now there was a finite temperature and negative specific heat capacity very near that Hagedorn. So you have to be very near, maybe scale you have to take a double scaling limit where the temperature approaches the Hagedorn in a way that scales with n, or maybe 1 over n. And in that very small region, you will see negative specific heat capacity. So basically this large n and appropriate scaling limits is what is needed to see physically this happening. So this heat capacity is arising purely from counting in harmonic oscillator systems, interactions, and people have been discussing how do we get to matrix in the 2 matrix model, for example, negative specific heat capacity, and it was conjectured that maybe if you start with actions, this e to the k will get modified, and maybe the interactions will produce negative specific heat capacity, which is of course the right thing to look for small black holes, which is a very interesting phenomenon in the dual ADS. But here you see from putting a constraint on the 2 matrix counting, look at equal numbers of X and Y matrices or Z and Z dagger matrices, and you get a feature. And as I said, we have this we were able to derive in ensemble. Would be nice to derive the energy at that transition in the microcanonical ensemble. It should not be too unrelated to this, but one needs to think it through. Analogous analytic calculations for the transition in the tensor model or matrix model are not known because we don't have set partition functions. We only have these group theoretic ones. But these group theoretic things show enough, with these curves that features are happening. So as well, for this audience, maybe this is the most familiar thing, that small black holes in ADS, they have a mass formula as a function of the radius and the radius of ADS, and they have a formula for the temperature, Hawking temperature. Using that, you can see similar behaviors at for small radii. There's negative specific heat capacity, and when the radius of the black hole becomes large compared to the scale, then you start getting positive specific heat capacity, and they build applicational thermodynamics. So based on that, so would be nice to take these quantum mechanical models a bit closer to more complex situation where you have this small black hole interacting with gravitons and things that are happening inside ADS. So you want to couple this to degrees of freedom to emulate whatever this small black hole might be coupling to. Obviously, you want to study time dependence, as Stoke, very interesting, and he also mentioned weak coupling n equals 4. So 2 matrix setup was very much right there. And the 0 coupling limit of n equals 4 super Young-Mills is 1. So there is a lot to explore. Yeah, hopefully there's a feature there that exists of systems, and it'll be good to map this out a little bit more systematically. And I'll stop here.
wondering what is the story in this permutation invariant when there are much more possibilities. So is there also similar universalities, or what is known about it?
So I guess the difference here is that, in the matrix UN, ON invariant setup, you can take the matrix and diagonalize it, and all the physics is in the eigenvalue distribution because the invariant functions, so yeah, all invariant functions are functions of the eigenvalue. Yeah, it's much richer, so the counting is much bigger. You have the counting of ones which don't reduce to eigenvalues. But there is another kind of universality when you study, Gaussian actions. There'll be some kind of central limit theorem for this multivariable matrix, and then in some situations, if you can argue that the physics interested in sort of permutation invariant, then you'll have some models that will approach this by the central limit theorem, this Gaussian model. So in some of the data science applications we have explored, world matrix ensemble that are well approximated by the Gaussian model. So that's sort of an analog that I can think of. I don't know if you have kinds of analogies, but yeah.
Other questions?
Maybe you would leave out all the fields for super youngers in some way.
Yeah.
So what do you expect?
So maybe one lesson, this two matrix setup is surely Hagedorn transition, which is something that is emulated, that does exist in the strong coupling. So, but then what we observed was that if you take the two matrices, but then just do a reduction
proceed to the second talk by Monica Gupta about consistency, bar holography, and computer safety. Please, thank you.
Okay, so I'd like to start by thanking you for inviting me to this workshop. It's very nice. Okay, so I will talk about something exact and something two-dimensional. So I fit in the line. So this part of it is partly based on work done in collaboration with my ex-student Silvia. And basically, I mean, this is some very technical paper where we take this something called JT bar deformed CFT, study to their symmetries from all sorts of perspectives, and then we do a precision holography, which is another like nasty calculation, but everything matches perfectly. So it's some hardcore thing. I thought I wouldn't kill you with all these technical details here, but spend instead most of the time trying to relate this work to Kerr CFT. Explain the status, as far as I see it, of the Kerr CFT correspondence, and also try to explain why I think cryptography is sort of necessary in that context. Okay, so general motivation starts with beautiful universal formula for black hole entropy, which strongly suggests that gravity is holographic, by which I mean it can be rewritten as a non-gravitational theory in one dimension less. And of course, we have this very beautiful realization of the holographic idea, and like really precise realization of it in the ADS-CFT correspondence. There are really two approaches. So one is the top-down approach, the original approach through which it was discovered, where you take some string theoretical objects, have very different descriptions. You take a low energy decoupling limit, and this gives a duality between specific, field theories and gravitational theories. And then what's very nice is that one can do precision tests with various precision tools. So that's one way to think about it. The other way to think about ADS-CFT is bottom-up, whereby any CFT that satisfies certain requirements, large n, maybe large gap, should respond to some theory of gravity in some higher dimensional ADS spacetime. And then sort of the universal features of the CFT, their structure, is coded in the asymptotic geometry. So the CFT symmetries are asymptotic symmetries of the ADS spacetime. The correlation functions are related to scattering. Thermodynamics is encoded in black hole thermodynamics. And basically, we don't really care what the theory is in this approach. If you change a little bit the gravitational action, you're just going to be changing a bit the CFT spectrum of the coupling, but really changing the structure. Of course, there's a good question if a CFT would those properties exist, but you're not changing the structure. So that's the general idea. What I'm interested in is going beyond the ADS-CFT, and this is kind of hard. So again, one can talk about top-down and both approaches. Top-down is via string theory decoupling limits. And here the problem is that there are relatively few concrete examples where you really use the asymptotics, so they may be weird. You might get flat space, but with a linear dilaton, maybe we don't care. You get sort of disparate examples. And even if they come in families, I don't think they've been systematized, so we don't understand universality classes of asymptotics in these non-ADS holography funny asymptotics. Now, oftentimes these theories, like when you want to use supergravity near the boundary, they're going to be very highly strongly coupled and non-local, so you have no clue how to track them down. An example is due to string theory. And also the precise rules for holography are not understood in general in this background. There's some work, for example, for DP branes, but there's really no general understanding for these top-down examples. So what people do most of study non-ADS holography is bottom-up. And here the focus is different. Pick a space-time that you like. You pick flat space, you pick de Sitter. I'll talk about warp. There's another bottom-up. And because, for example, in these two cases, we need the decoupling limit from string theory that leads to them, so it's simply assumed there's going to be some sort of field theory dual. That's an assumption. And then it is assumed that, you know, no matter what action you choose, you're going to get sort of the same universality class of theories. And then to infer the properties of disputative dual QFT from the spacetime. So it's the same symmetries are asymptotic symmetries and so on. The problem with this game is these quantities can be ambiguous. Like the asymptotic symmetries of the space depend on the boundary conditions that you impose, but this is not something that you know. So even the entropy is ambiguous because that presumes knowing the relationship between your bulk time and the boundary time, and there's not something that you know. So there's actually a lot of ambiguities, and there's nobody telling you that, okay, choices over here, that whatever answers you get from this are going to be logical self-consistent. They're going to actually correspond to a theory. So that's a little bit, say, problematics of non-ADS holography. So what I'll do in this talk, I'll try to examine challenges of non-ADS holography with one example, which is the Kersey effectiveness. It's just an example which has a lot of problems, so it's. And as we'll see, it's a really important issue is that of boundary conditions. I think that's the main stumbling block. We don't pick boundary conditions for this correspondence. And given this state of affairs, I'm going to argue that more input is needed, like independent input is needed in the holographic dictionary. Ideally, some knowledge of what the dual field theory is or what its properties are. And then I'm just going to produce some field theory that I think has the right flavor and develop it. That's the J.T. Barr story. And then try to see how this story is going to reflect back on Kersey. So is the logic clear? Okay, so let me just briefly talk about Kersey-FT. So the Kersey-FT correspondence, I mean, one can say it's like an example of bottom-up holography. You knew nothing about the space-time, and then you come up with methods, asymptotic symmetries, and so on, and propose something. So what it does, so one looks at the very near horizon region of an extreme curve black hole. So this is known as the geometry, and its peculiar feature is that it contains a factor, and there's a U1 fiber over this ADS2 with a variable, fiber size. This whole thing is known as warped ADS, either a squashing or a stretching of ADS, and then some other angle. And the Kersey-FT claim is like the Kersey-FT set of ideas is that you just come up with some boundary conditions on this geometry, which come out of nowhere, and then you find that you have sort of an infinite set of symmetries that enhance this U1 right. They form a Virasoro algebra with some central charge. And then you take the central charge, you stick it into Cardy formula for no particular good reason, you get to reproduce the Becker-Stein-Hawking entropy. Another thing that's nice about this is that it doesn't just work for extreme curve, it works for all extremal black holes, this procedure. Now, of course, one has to look at this for a more modern perspective. So we have since learned that exactly extremal non-supersymmetric black holes, you cannot really rely on their job. So in order to trust the classical approximation, we should consider instead near extremal black holes. And a lot of the features of this, Kersey-FT business are actually related to near extremal behavior of the black hole, and many of them are captured by a JT gravity model that just has to do with the reduction to 2 dimensions. Okay, so maybe one consider something a bit more general than JT gravity, but that's roughly it. So so this JT gravity model can capture a lot of the physics, but one thing that I capture from Kersey-FT is the entropy at extremality. So it can reproduce the entropy above extremality, but not the entropy at extremality. That's the right movers over here. So this is what I'm going to call the Kersey-FT problem. How do I understand? Yeah, so I should define it a bit better. So when I go to the JT gravity description, I want to talk about that S naught and ignore the one loop correction. I was but from the JT-gravity perspective, I think if I have a sort of a decoupled words perspective, I have a good meaning of entropy, and then I can take a limit.
There's a factor in the technical, but I will not call it.
I agree that's a slope. But do you have a short correct characterization that you can express in a few words? What do you want to call it? I'm happy. But I mean, in the full description, it should be some sort of entropy. Okay, fine. Okay, we can discuss about it, but besides Alejandra, other people have understood what I mean. Maybe an analogy that's helpful when you look at asymptotically you have black holes, you can meaningfully talk about the entropy, go to near extremality, and you have the same issue. So it's analog of the extremal BTZ entropy, but transform to this. Okay. Okay. So basically, what the Kerr-CFT problem that's not included in this JT-gravity, that's not explained by JT-gravity, is to explain this quantity, and in order to approach it, it's actually better to not work with a very near orbit of the extreme Kerr black hole, because of this focusing of the energies. It's better to go to some sort of toy model where we can have like proper dynamics, proper decoupled thing. So actually, for me, Kerr-CFT from now on will just be warped ADS. Which has to do with this factor over here. Okay.
What I understood that you meant was part of the entropy is not linear.
Exactly. Yeah. Okay, very good. So if we're to draw a little diagram of what this bottom-up analysis for Kerr-CFT is the following. We seem to so the isometries of the solution are SL2 left times U1 right. The U1 right gets in right. The entropy sort of looks like Cardy. And then people have also done a scattering calculation. And for two correlation functions, you get some CFT-like answer with the conformal dimensions depending on the momentum along this U1 direction. So for people who, I think this should be well known, but basically this comes from, so the people who did the calculation were these people. It's a bit confusing that in the abstract they claim that the scattering amplitude is precisely by a dual two-dimensional conformal field theory. But if you actually see what they write down in the paper, so this is the 2D CFT answer, where H right are the dual operator conformal dimensions, and the specific expressions that have for left and H right actually depend on the momentum along the U1 direction. So basically, the correct interpretation is that you're getting an answer that's CFT-like, but actually non-local. But this non-locality is of a highly constrained form because it does look CFT-like. Okay, so that's the structure. And this whole thing is highly preliminary because, as I said, I don't really want to work in this very near horizon region, and I should warp the DS toy model to figure out what's happening. Because one of the things I want is to explain this the entropy. Okay, so have there are a lot of toy models to study that are really CFT correspondence, and one can again classify them as and top down. And among the bottom-up models, the most famous are topologically massive gravity and new massive gravity. So these are three-dimensional theories. They're non-unitary, so they have ghosts, so they're not exactly consistent theories. Also, you can have 3D gravity coupled to massive vectors. So all theories have warped ADS solutions, and the warp parameter is determined by the couplings in this Lagrangian. And black hole solutions corresponds to the quotients of global warped ADS. They work. You can also come up with top-down toy models for CFT, And these are consistent truncations of string theory to 3 dimensions. We only know of one properly decoupled background. This corresponds to horizon geometries of higher dimensional near extreme black holes. So they have maybe a more direct relation to KERR-CFT. And if you look at the 3D line, they resemble massive vector theories plus a bunch of scalars, but the couplings are very, very finely tuned in this 3D Lagrangian. Fine tuning is such that what happens with the solution is that the warped ADS parameter is no longer related to the couplings in the Lagrangian, but it's actually determined by the temperature. So black holes are not quotients. Okay? So the first conclusion that you can draw from here is that there's really no universality for the toy models for warped ADS, unlike for what is assumed of ADS. You can get very different behavior depending on how you choose to model. And in particular, these ones which come from top down, you know, it's I guess hard to cook up an action. You know, couplings are such that they will produce this behavior. Okay, so they're very unusual among all the 3D actions that you could be writing down with warped ADS. Okay, that's one point. Then you can go ahead and study the behaviors, 2 types of toy models. So the bottom up, by TMG, okay, so this is what black hole entropy looks like. This is mass, this is angular momentum. The asymptotic symmetry group basically enhances the SL2R isometry of the background to Virasoro left, and the right moving translation to a left moving Kac-Moody. So this is a peculiar thing. This structure, this enhancement structure is called the warped CFT structure. And then central extensions, the Yuan Kac-Moody level is negative, so the theory is non-unitary. This is no big, surprise because TMG has ghosts. And then one nice thing about it is that one can show that theories with such enhancement pattern possess some sort of warped modular invariance, and they have a universal entropy. And this universal entropy, this modular invariance, precisely explains this. Okay? And scattering, okay, you get something that depends on the U1 charge. For them, U1 charge is energy, so you get non-local stuff. The top-down models produce very different results. The entropy is Cardy, at least when no additional U1 charges are. The asymptotic symmetry group, depending on what you do, you can get Virasoro left, you can get Virasoro right, you can get both, or if you do something else, you can get warp of things. So it's really, really inconclusive, and this is lack of knowledge of what boundary conditions to impose is. So I think one cannot conclude anything. Scattering is again consistent with non-locality on the right. Okay, so because of these, these results, so people, what did I do? People talk about at least 2 different types of dual theories to warped ADS backgrounds. One class is known as warped CFTs, which are putative 2-dimensional QFTs, which have this enhancement pattern, SL2 times U1, 2 Virasoro left times Kac-Moody left, all these right translations. I say putatives, so actually, as far as I know, the only concretely known examples are 3. Maybe Alejandra has worked on this, but I don't think there's anything else known. So you have to show that they exist in the interacting case, and they're conjectured holographic ADS. This basically follows from staring at the asymptotic symmetry. It depends on the boundary conditions. And in these holographic setups, you tend to get negative level. As you see here, even in string theory, you get negative level. So non-unitary and non-local. And I should say that the simplest proposed holographic realization of warp CFT is actually just pure ADS3 gravity with some boundary conditions called convergence, where you basically make fluctuate the plus component of the boundary metric, and you freeze what would have been the right moving stress tensor to a constant. And then you can see that the asymptotic symmetries are precisely this Virasoro left times Kac-Moody left with, with the standard Virasoro central charge and the negative level that depends on this L bar. Okay, so that's what's proposed. For the constructions, people sometimes talk about dipole CFTs. This is related to this one non-decoupling limits for warped ADS background. String theory is related to the dipole deformation of the D1, D5 system plus flow to the IR. Completely intractable, so you have no idea about the properties of the theory. However, what you get is that this should be some irrelevant deformation of a 2D CFT that leads you into a UV complete theory. That's very, this is what string theory leads to, and it's theory naturally local and conformal on the left because you have 1, 2 and non-local on the right. Okay. Very good. So this is the current status. So you have some bottom-up approaches. You get something like this, but there are question marks everywhere because we don't know the boundary conditions. And the top-down, you get this idea that this irrelevant flow that gets a UV complete theory, but it's completely intractable. And what I wanted to point out, the toy model for your holographic setups is actually important. Have select boundary conditions, so it would be nice to get some additional input into this problem, because otherwise we cannot make progress. And the idea is that having some explicit field theory toy model for the correspondence can help. So what is this toy model basically realizes this sort of flow. It's an irrelevant flow out CFT that gets you into something UV complete. And it's an exactly solvable theory, and because of that, we can just actually compute what all of these things are. And yes.
Since the CFTs are non-unitary.
Which CFT is non-unitary?
Previous one, you have negative levels, things like that.
Well, so I guess what I'm trying to say is that I'm really not convinced that this theory
Even worse. Making a comment about this RZ flow, can you say things about C theory and things like that if you don't have unitary?
Okay, so this is why. So the non-unitary stuff was on the bottom up. Okay? The non-unitary stuff with the K negative, this is in the bottom up, in topologically massive gravity, all these sick theories that it's not a problem that they're non-unitary because they already had ghosts. On the string theory side, you'd better expect something unitary.
Yeah, but I see a minus there.
Well, this is some particular boundary conditions that were chosen to produce this asymptotic symmetry group. But what I'm trying to say is that you have no clue what the boundaries are, and there exist boundary conditions where you can just get Virasoro with the standard central charge. So I think there's no. So what the boundary conditions produce, warp CFT kind of stuff, they tend to give negative level. They look non-unitary, but it's absolutely not clear whether these are the correct boundary conditions. It's also absolutely not clear whether these are valid toy models for anything that you may be interested in.
Boundary conditions that turn the sign positive?
Yeah, so I think this is not sort of the way to approach. I think you'd ask, what are the correct boundary conditions for the system? It's not whether you can engineer, because you don't know whether a consistent theory exists for any sort of boundary condition that you might want to impose, or any toy model that you may want to work with. Okay, good. So this was supposed to be the status. Any questions? No. How much time do I still have? Oh, sorry. Okay, so I must have spoken very fast. Okay, sorry. In the D1, D5 CFT, you can, well, it depends. You can sometimes identify it. So this 1, they're supersymmetric descendants of 1,1 carries. And those are 22 of them in the K compactation. And one of them is an holonomy singlet. And that's actually the one that's most closely related to the Myers-Berry black hole, so you can actually identify it throughout moduli space from the strong cupping point to the wall before. The other guys, there's some. they don't mix. It doesn't mix for 1,1 chiral primaries, whereas the other guys can mix with each other. But yeah, you know what it are. But I mean, so there's not identifying what the guy is over here. The problem is how are you going to flow in such a way that the remains UV complete? You know, this is very hard. It's clear that it's not a JT deformation because the JT bar one is actually in the vector of SO21, or some combination of vector and singlet. This is a warped ADS spacetime. So actually, if you go to the IR, it looks like ADS3, and in the UV, it looks like this non-normalizable deformation. Yeah. So this is where it comes from. But in the higher dimensional deformation, you can see explicitly that this deformation is very special, is refined, and actually preserves UV completeness. That's for deformed n equal to 4 super Young means. For this case, you cannot say anything from the gauge theory picture. Okay, so this is sort of the status. These analyses are sort of ambiguous, and this analysis is sort of untractable. So we want to do a toy model and see what it gives us. The toy model, it's called JT bar deformed two-dimensional CFTs. So what's the JT bar deformation? It's some irrelevant deformation of two-dimensional QFT, which is constructed. So it's an example of a so-called homological deformation, and it's constructed from a bilinear of two conserved currents. So in this case, it's going to be a U1 current, J, and the right moving translations, which is T bar. Okay. So, but more generally, what one does is some antisymmetric combination of the two current components, and then this turns out to actually have a very interesting, when operators together, because of this, the way this combination works, you're going to get some with a constant coefficient, and everything else are going to be total derivative terms. So this defines for you the Zamolodchikov operator, which has very nice factorization properties. And then you take it and you add it to the action in sort of incremental fashion. So you add it in the undeformed theory, then you recombinate in the deformed one, and you add that operator and so on. And this is actually a way you don't need to add anything else. So that's the magic of Smirnov-Zamolodchikov. And people usually study, like, there are two deformations that are like studied. One is TT bar, where you take the two currents to correspond to points of the SER. And the other one is JT bar, which is of interest of me now. So, as I said, here one current is a U1, and the other one is the right moving stress. The deformation, therefore, has dimensions 1, 2, J bar. Therefore, it breaks Lorentz invariance. It actually preserves LCL to our right. So after you add it incrementally to the action, it's going to end up with a theory which is local and conformal on the left and non-local on the right. This is precisely what we are calling a 2D dipole CFT. So it's an example of a 2D dipole CFT. The nice thing about it is that these deformations are argued to be UV, and JT bar is exactly solvable. So, we can ask our questions. Okay, so it's solvable. So what about it? So it turns out that all observables that could be computed are simple, universal, local deformations of the original CFT observables. So the way you do these calculations, most of the time, you put the theory on a cylinder of SR, and you look at the flows of states and of energies. And at least in the classical limit, this operator is exactly known. So what do you find? So here I'm writing my favorite observables. What do you find? So for example, you find that so you can derive the exact spectrum, and then from the fact that the deformation is adiabatic, so the number of states really doesn't, you can derive a universal entropy, which takes the Cardi form. So it reduces to Cardi if the U1 charges are 0, but otherwise it's different from it, and it's universal. This is symmetries are obtained by you take the Virasoro-Kac-Moody generators of the original theory and you flow them. So the algebra is going to stay the same. However, what's special that's happening is that actually these Moody generators are not the natural generators, quasi-local generators that act on the fields in your theory, but they differ from them by some like spectral flow by lambda times the right Hamiltonian. So if you want to look at the actual symmetries, their algebra is nonlinear. And this kind of weird realization of Virasoro-Kac-Moody is actually no locality. You can also do correlation functions. For that, you have analogs of primary operators. Turns out they exist, and they're very nice. And you find that their correlation functions are entirely determined by those in the seed CFT. And if you look at 2- and 3-point functions, they look exactly like CFT momentum space correlators, but where the dimensions have been replaced by some momentum-dependent combinations. So it exactly fits with what one was finding for the black holes on the gravity side. It's a different function here, though. Okay, so the black hole. So it's the same flavor, but I mean, this is double trace. Those guys are single trace, and no, it's but the phenomenon, it's yeah. No, yeah, this is dual to ADS3 with funny boundary conditions. It's not part ADS. Yeah. Okay, good. So now, okay, so we could compute all of this stuff in the field theory directly, very explicitly. And now we wanted to say what it does in how to see all these features. So as it turns out, the holographic dictionary are deformed CFTs. You can just write it down very simply, because JT bar is a full trace deformation from the holographic perspective, and therefore responds to ADS3 gravity with mixed boundary conditions. Very simple. To model it, you need 3D gravity coupled to 2 Chern-Simons gates. You have both a left and right moving ion current. And then you can do Haber-Stratonovich to see how the sources, field-bind and gauge field in the deformed theory are related to sources and waves in the undeformed. It's the standard stuff. The punchline being that the boundary conditions bulk fields, which correspond to just fixing this guy and this guy, are entirely determined by the field theory. So from the gravity side, you just write down your model to model correctly what this guy does, and then you're done, and everything is being told to you. And you're just following algorithms for how to compute stuff. And if you want to write down, if you fix this to be 0, then this is the most general, astrictly whatever JT bar solution. So it's parameterized by 4 functions: L of x plus, J of x plus, L bar of some field-dependent coordinate, and so on. Okay, and one thing to notice is that if we make this L bar to be a constant, the gravity part is identical to the CSS solution of pure. Okay, so now, okay, so one can take these solutions and all the charges, all the entropies, all the blah, blah, you get perfect match to JT bar deformed spectrum. I won't spend time explaining. And then you can also do the symmetries, which are sort of interesting. And so as I said, the symmetry generators are this JT bar flow with the JT bar operator that flows the states, which down exactly. So we can just solve in the classical limit for the flow generators. And then we do this nonlinear redefinition in actual, quasi-local physical generators. This is what they look like. So we have some generators of Virasoro and Kac-Moody left. These are standard. And then for the right-moving guys, they're actually field-dependent coordinate transformations. So you're shifting the right-moving coordinate by the bosonization of the current. Importantly, you have to subtract the 0 mode of this boson. This is what the flow to do. And this is very important in order for the algebra that you get to be with U1 charge quantization. If you don't do it, you get crap. So what we did with Sylvia, we took this and we translated it to the Lagrangian formalism. to see what the corresponding transformation look like. That for each of the right-moving Virasoro, if you wish, and Kac-Moody, we have to accompany each shift by a large affine transformation. So one that goes linearly in the coordinate. Again, we can explain with a coefficient that depends on the charge. So these are very equations, but they are necessary in order for the U1 charge quantization to be obeyed. We can understand this in the Lagrangian formalism. Then we can do the asymptotic symmetry. So we take the boundary conditions that were given to us from the field theory. We solve for the most general Diffie and gauge transformations that are compatible. They're parameterized by 4 functions. One important thing, we have to require the gauges to be periodic. That's basically implementing this U1 charge quantization. And this forces the sum of the functions parameterizing the solutions to have winding. And that winding, when we compute the asymptotic symmetry group, will give rise to nonlinear terms, which precisely reproduce the nonlinear modification of Virasoro-Kac-Moody that we can see from the field theory side. Okay, so we get perfect match to symmetry algebra field theory. And as I said, all these asymptotic symmetry group calculations are nasty. They're obtained by just doing this, algorithmic Barnish-Brand formalism. What's important is having the boundary conditions and the quantization condition. That's the field theory input that we use, and then everything works out using the given formalisms. Okay, so the holography part. And maybe I can spend 1 minute commenting on CSS boundary conditions. So as I said, say we set J bar to 0 and we take L bar to be a constant, then the metric reduces to the general Comparison-Strominger solution in pure gravity. And a natural question is whether the dual to CSS can be understood as a subsector of this JT bar deformed CFT. And the answer that we find is no. And the reason is because even if in this limit the metric reduces to the CSS metric, the gauge not, and actually the gauge fields contribute to the conserved charges. So we get very different answers for the asymptotic symmetries. Yeah. So what CSS see is just this piece, and this is why they have to fix L bar and get some, state-dependent level and so on. Our charges are the sum of all of these, which are like trivially integrable. So we find a state-independent Kac-Moody level, and everything works nicely. So it's not, one can try to give an interpretation to this. My personal interpretation is that maybe this CSS boundary condition, maybe it's just not a correct toy model. In the sense that if you really want to do some double trace deformation of a CFT by something that only depends on the stress tensor, because if I have a gauge field, then I have to put on scaling in the bulk, then there's no way to write such a thing. So maybe if I really want to implement CSS like boundary conditions at the level of the metric, maybe I really need to turn on the gauge field, and then I get very different answers for what the asymptotic symmetry group is. Sorry, what does this mean? I still have 10 minutes. Okay, very good. Sorry, I was rushing because I thought I'd be out of time. Okay, so one can discuss. I don't have a very full argument, but to me it looks that maybe this is simply not a good toy model from which to extract these conclusions. Okay, so this being said, okay, what does this precision match between gravity and field theory, what can it teach us about our quote-unquote CFT? Well, so one obvious conjecture that you can make after all of this is that the observables of this curve quote-unquote CFT are precisely the J bar observables. By which I mean, for D you should get JT bar modified Cardy, and for the symmetries you should get this funny Virasoro-Kac-Moody that acts in a funny way. And if you remember what I said when I reviewed the curve CFT correspondence, what people find currently. And part of the reason is because people weren't really turning on the C1 charges. So maybe if you start going to the theory construction and turn on the C1 charges, maybe you can see whether the Cardy or maybe JT bar modified Cardy. problem with doing this is that one doesn't really get worked at the decoupling limit. So we tried to do it with my student for a really long time, couple background, and we didn't get to work. And the other ones are not decoupled, so we don't know whether the time is the correct time, and you know. Song and Luis Apollo, they have a proposal for one of these backgrounds where they can get JT Bardi from thermodynamics. It would be nice to argue that this is the correct result, not that you can get it. But one of these backgrounds, they can get this. Question is like, okay, how can we determine, how can we find the correct boundary condition, and then see whether the symmetries look like this or not. And one point that we have tried previously in the relationship between TT-bar deformed CFTs and asymptotically linear dilaton background was that if you know exactly how your background depends on the black hole parameters, so if you know exactly your black hole phase space, you can try fixing the asymptotic symmetries, comparing the radial symplectic form between units of the metric due to the action of the asymptotic symmetry group parameters on the background, and the variations that take you in between the various black holes to be zero. So this is basically saying this lead derivative do something in the phase space. This guy, I know that it's in the phase space. Radial symplectic form for two things in the phase space should be zero. That's okay. That's like the symplectic pairing of sources and waves. And here I'm claiming that they're true. So if you do that for the linear asymptotically linear dilaton background, you find precisely the TT-bar asymptotic symmetry group, which again has this type of nonlinear structure. And as far as I hear, so my ex-student was looking into this for the Wei Luis background, and she seems to be finding the JT-bar structure. The question is, is this the correct way to be finding functions for your non-ADS holography question? And okay, so this is end question. How do we fix boundary conditions in this non-ADS holography? How do we fix the parameterization of the backgrounds? I'll leave you at that. So to conclude, so what I talked about, so this bottom-up asymptotic symmetry group-based approach is a powerful tool to obtain insights into non-ADS holography. I don't think there's any question about that. In doing so, one has to deal with all sorts of ambiguities. One must be careful about the choice of gravitational toy models to draw one's conclusions. Therefore, I argue that input from top-down approaches and QFT top models seems necessary to guide these powerful bottom relations. And I gave the CurCFT example, and presented some way to maybe proceed that may allow to fix us. But I guess the question that I would like to leave you with is whether is there any universal rule for how to find the appropriate boundary conditions on a given spacetime in some holographic, non-ADS holography. Yeah, so
I was wondering in the area CCCP setup that you have, do you also have a similar interpretation? Is also from TST in this case, or
yeah, so the bug indeed obtained via TST. Actually, all of the string theory setups are obtained via pseudo dualities. But the only actually I think lands you on a decoupled geometry is when you do the Ramond background. But yeah, they're all at the worksheet perspective. Yeah, they're purely NS, so one can just solve the worksheet model. Well, so people actually have, yeah. Maybe I some backup slides. I don't know how useful. Okay, yeah. So for example, if you take this setup, ADS3 times ADS3 with pure NS, and then you do TST on time and space, like in ADS3. Then you get a solvable worldsheet sigma model, and then if you look at the long sector of the sigma model, you find the spectrum precisely in the single trace JT bar. Okay, so this is something that has been both for JT bar and for TT bar. For TT bar, sorry, for JT bar you have to take 3 directions and 1 is on S3. For TT bar you have to take 2 directions in ADS3, and then you get similar results. The only problem with this is that, as you well know, this you know the purely NS ADS3 background, sort of a singular point in the space of background. So the ADS3 point is not very clear what these long strings. I mean, people, but from a CFT point of view, it's not very clear what they do. And his connections to single trace TT bar and JT bar, they work very nicely in this sector. But I don't know what happens if I want to go to a less singular point in the moduli space of the initial background. So, yeah.
So I guess I mean in the last question that you posed there, right? So
I would expect you to have an idea.
I was just going to ask, like, I mean, you mean, and also you take into account, like, I mean, the constraints that come from the quantization of the bulk theory, like, basically that would impose some constraints on the possible boundary condition. Like, I mean, if you try to for theory, right, I mean, like, that would lead to some constraints of the boundary condition.
So you think that it should be doable just in the low energy by being a little bit more careful. So what people normally do is they take the charges and they demand them to be finite, integrable, and conserved.
Only classical from the bulk point of view, right?
You think if one just goes to semi-classical quantization, that should be enough to in the bulk?
I don't know if it's enough, but I mean, certainly it's going to be more liquid than just.
Yeah, I think it's a very interesting question that should maybe, you know, what are the rules for boundary conditions? So if you just use the rules I knew a minute ago, you get way too many possibilities.
Right.
So it would be nice.
But I mean, you know, there's work by Anderson, like Witten, also for ABS boundary conditions. That you get restrictions once you go to the quantum level. So it's not, I mean, naively look okay at the classical level, but I mean,
okay, it's I mean, if that fix it and restrict it, then it would be nice to classify. For example, for this example, I mean, of work, so maybe it's, yeah, it would be nice to understand what.
questions?
Yeah. Have you thought of like taking maybe a different perspective of thinking of this warp geometry as the IR instead of taking it as the D? So for instance, let's say that this next here inside the ADS. We have a Horizon geometry in that case, it builds something. It looks like that. But then the UV will be a CFT3. So
I mean, the question
is that helpful, like to think of like, oh, I'm deforming the CFT3 by something that takes me to the IR, and I get this non-local.
Well, it's a bit tricky because, right, the type of warped ADS geometries that you get from that flow are in the very near horizon. So there is no energy limit of my dipole CFTs. So I don't know if.
But in some sense.
But the answer is no. I haven't thought about it because I would guess that the flow is very hard to track down. But yeah. Yeah, I should think of whether you're supposed to. Yeah, one should. Yeah.